think that's drawn right. And they want V out over, they just want what V out is. So for this one, we're going to do it. Can you all see this is V2 and this is V1? That's R1, R2, R3, R4. Is that correct as drawn? All right, can you circle the book, class? Okay, good. So if we want this, the game is this. You got to find a voltage on one of these two terminals, right? You need a voltage on the input because you know whatever the voltage is on one terminal, it is on the other, and then the problems usually fall apart. Do you see what I'm doing here, class? So work with me. You see how this one right here, V1 is really this, right? It's a voltage between ground and where the V1 point is. Now, if you see that, how much current flows into the positive terminal? Class? 0. Yeah, get used to it. If you say it, it'll stay with you. I promise you, it's much better to repeat and maybe you may be, I don't know, unwilling to do so, but it will help you. If you're in the armed forces, you do a lot of that, I think. Because I've been on the carrier at Eisenhower, I learned my lesson well. Without repeating this. Anyway, no current in there. That means this is a simple loop. You follow me? It means the voltage here, and I'll just call it VR4, can be found very straightforward. You can say VR4 is really V plus, right? Because that's the voltage on the plus terminal with respect to ground. And that's simply equal to the actual input voltage, V1, times the ratio of R4 over R3 plus R4. I'm calling that just V plus. Does everybody agree with me there? All right, V plus is a function of V1. And if you give me exact values for R4, R3, we can calculate the percentages, right? So that's not a problem. That voltage, V plus, or that voltage right here, is also right here. There's no difference, correct? Now, if that's that voltage, we also know the current going from V2 through R1. Now we know this current, and I'll just call it I2. I2 will be equal to V2 minus V plus over simply R1. That's equal to V2 minus V plus is that minus V1 times the quantity R4 over R3 plus R4 divided by R1. Agreed? I'm just going through the motions on this one. Now, once we have that current, does everybody see what I'm doing here? Who asked this question? Okay. All right, if we've got that current, how much of that current goes through the negative terminal, into the negative terminal? None, right? 0, all right? Get used to that. I promise you we'll have people figuring a way for current going in there. There's something magical about input terminals requiring current. It's none goes in there. All of it flows this way, right? And if everything flows that way, that means this voltage here, VR2, is just equal to, which I'll call this I2, times R2. Agreed? Go with me? Yeah.
So, is there any significance to the plus and minus of the op amp, or is it just sort of arbitrary?
Well, I wish that you had those. If you had an advanced circuits course, it'd be easier. Advanced analog circuits course would be easier to explain. The negative is usually referred to as the inverting terminal. The reason is any voltage that comes in here, with respect to these two to the output, is going to be an inverted. It'll have a negative sign, all right? If it goes in positive, it comes out negative. Here, this is called the positive terminal. If you have, and I do know where you're saying, it seems you could reverse it. And in truth, you're right about that, but the way it's set up, the way I'm putting the positive on the bottom always, then if I put a voltage here and I put, say, a resistor down here and a resistor this way, this has no way to feedback from here. It'll give me a positive output. But the truth of the matter is there's other reasons for this, and it has to do with the operation of the proper operation without going into saturation. That's way beyond the scope of this course. For now, there's not a real difference, but negative is usually inverting, positive non-inverting. All right, now, y'all agree that's I2, class? Now, and that means this voltage right here is just I2, R2, all right? Now, I'm just gonna say that, since that's I2, I'm gonna go ahead and put V2 up here. And V2 is just R2 times I2. So I can take R2 over R1, right? When I take R2 times that, and then it's gonna be times the quantity V2 minus V1 times the quantity R4 over R3 plus R4. And now I have V2, the voltage from here to here. Agreed, everyone? Class? Can you all see it in the back, guys? All right, now what's my voltage on the output? This is V out. Output voltage is always taken with respect to ground, this being plus, ground negative. So I look at V out, and what do I see? Now work with me. I always say start at the negative terminal, right, of the place you want the output voltage. Correct, class? Or anyone? Yeah?
Could you re-explain the V2?
Could I what?
Could you just re-explain it? You got your V2.
Yeah, I took I2, right? I2's flowing through there. It's this size I2, right? Times R2. And I2 is up here. It's V2 minus V plus over R1. You all see this, guys? It should be pretty clear, right? Once you get the current, current times resistance is voltage. Now when I look for V out, I start at the negative terminal, right? And I come down in here, and I want to find the voltage here. That's V plus, right? Is that class? With me? V plus, and then it's going to be minus V2. You agree with that? So I'm going to have V out is equal to V plus minus V2. What is V plus? It's what VR4 is. It's V1 times the ratio of R4 over R3 plus R4. It's that minus V2. Minus V2, and this is V2, so it's minus, and it's going to be R2 over R1 times the quantity V2 minus V1 times R4 over R4 plus R3. And now, if you wanted to get V1 minus V2 times something, first, there would have to be, does it give you values for R4, R3, R1, and R2? Any problem?
It tells you that R3 over R4 is equal to R1 over R2.
R3 over R4 equals R1 over R2. Is that right?
Yeah, I think so. And then it asks you.
V naught is equal to R2 over
Yeah.
R1.
Well, they make, if this is the case, find out with V naught minus V1 times, they want to find out with V naught is right. All right, if that's the case, then let's see. If you got R1 over R2 equal to R3 over R4, I'm going to put that right here. I've got R2 over R1, and 1 over that would be, see, I got R1 over R2 there. Here I have R2 over R1. Take 1 over that. That's R4 on top, R3 on the bottom. You agree with me there? Everyone? Now, at that point, what I'm going to do is get the coefficients. So here, when I have V out, I've got the coefficient of V1, and the coefficient of V1 is R4 over R3 plus R4. That's just this coefficient. Then for V1, I have minus a minus, right, or plus, correct, class? And did I get that ratio right there? Is it R3 over R4 is R1 over R2?
Yeah. 1 over 2 is equal to 3 over 4.
Okay. Then if we got this right, and this is R4 here, and this
It
is
also
R.
gives you a V naught. It tells you that V naught is equal to the quantity of R2.
Yeah, no, that's what you gotta prove.
Yes.
Alright, so, but is this R4 and this R3 in the drawing?
Yeah.
And is this R2 and that R1? Okay, then, yeah,
Just real quick, on your V2, the R2 over R1, why do you do R2 over R1? Why is it not just R2?
for V2 right here,
Yeah, well, why is it not R1?
it's I2 is right here, right? I2 is this,
Yeah.
times
So I get the first part.
R2, so it's times R2, so the R1 right here is in the bottom, R2 is on top. This is just,
Oh, you took-
that
oh,
is
my bad.
I2 times
Yeah,
R.
you took the bottom one. I got you, I didn't notice that.
Alright. So let's see if this works. It's gonna be that plus, because it's minus, a minus is plus, and then it's gonna be R4 over R3 times R4 over R4 plus R3. That's V1. Minus, and then it's gonna be R4 over R3 V2. Now, I hope these things reduce. Let me just see. Okay, I can take out R4 over R3 out of both of them. Here and here it's common. So I have V out here equal to V1, and then R4 over R3 plus R4 is common to both, and I have 1 plus R4 over R3 minus R4 over R3 V2. And now, let's see here. For this one, now we simplify here. Let's see here. If I divide top and bottom of this one, top and bottom by R3, I get this is going to be 1 plus R4 over R3, right there, and this is going to be R4 over R3. I'm trying to show you this. Y'all see what I've done here? Divide top and bottom, that first one by R3, right? Now you can see that this and this cancel. Y'all see that? Class, can y'all see this right here? Right? 1 over R4 plus R3, 1 over R4 plus R3, they cancel. Correct, class? All right, I'm going to cancel. Now you can see I have R4 over R3, and I have V out here, will therefore be equal to R4 over R3 times V1 minus V2, if that's true. If that's true. And that's the way I got it. Are you okay with that, everyone? How many see this? It's not a hard proof at all. It just is manipulating a few things. Agreed? For the record, I don't ask for proofs in this class. I ask for analysis. So I'm going to ask you to analyze circuits with real values, just so you know. All right. But this is a typical kind of question that you get because it takes you a step beyond. It makes you think about values that will give you certain output properties. Here, they want the output to be directly proportional to the difference in the signals. That's what their goal was. If you make the ratio of R3, R4 to R1, R2, it will be. That's the goal of this. Any other questions about this? I'm going to do 32 about this problem. Anyone? Okay. Agreed? I'm going to try this one. All right. You can see it's not a hard problem, but it does require you to go a step beyond the usual because now you have to manipulate it and prove this. Proofs, by the way, most of the time land in the College of Math and Science. If you do mathematics, I had an honors person. It was a special topics math class, and I remember everything was proof. And it's good to do that, but most of the time in engineering, what they'd say is, we want the output to be directly proportional to the difference in V1 to V2. What values of R3 to R4, R1 and R2 make this happen? You would come up with the ratio type thing. That's what they usually ask you. All right, next question, next problem. I'm going to do 30. Now, somebody asked me about this problem in my office, but I have no idea the person's name. Well, wait a second. Is Price here today? Is it Price? Was it you? Yeah. I think it was you. This is 930. This is a good problem. Anybody try 930? How many tried it? All right, you guys get it? I mean, the answer is, okay, good. This is a good problem though. So what they do is this, they have ground here, then they have a resistor, R3, or is that R3? Yeah, I think it is. They have an operational amplifier. This is plus, this is minus, right here. Then they have a resistor going right to the output here. And they have a resistor here. They have VN. They have a resistor here. I think this is R4. Correct me if I'm wrong on this, class. This is R1, and then they have R2 here. They give you values for this. We'll get that in a second. Put the values in a second. But this is the basic thing they want. They want the output voltage. All right. Now, here's the challenge. You're used to seeing something on the inside circuit, something on this side tying the ground through a resistor, right? There isn't one. You all see that, everybody? There is nothing goes to ground anywhere but here. All right. So in a sense, it does tie to ground there, but you don't know the current from V plus to here. Everybody see this? So here's how you get this. These kind of problems take you to the next level. What you have to find is the voltage on the plus or minus terminal. Where do you actually start on this one's a good question. And the answer is you don't start right there at VI. You start here, V0. Now, listen to me. You know that V0 here is going to cause a current to flow, I, and it will flow this way. And none of that current will flow into the positive terminal, so all the current flows here. You all see the path of current, right? If no current goes in there, you see these are just two series resistors, right? That means if V out is there, I can find this voltage by taking the ratio of I'm taking V0 times R3 over R3 plus R4 will be the voltage here to here, right? So VR3 will be equal to V plus, and that will be equal to simply V out times the quantity R3 over R3 plus R4. Do you all see that, everyone? How many did? Right. This is a little different problem. You had to use the output voltage, which is unknown, to get the input, the voltage on the input terminal. Now, that V plus is the same voltage here, right? Agreed? You know the game from here on if you've been paying attention. Now, our next job is to get the current through here. And I'll call that I1. I1 would be equal to that voltage, Vn, minus V plus, over R1. All right? And V plus is up there, so it's equal to Vn minus V out times the quantity R3 over R3 plus R4, right? All over R1. Y'all agree with me? Remember, there's nothing tricky here. It's just going through it, making sure you understand the steps. And you have to use your head on these things. You have to be a bit clever sometimes. And it's not just brute force analysis. So if I come down to here and I got that current, I know that current goes, none of it flows in the plus, all of it flows this way, so I can get the voltage there. Do you agree with me? Just take that current times R2. And this is simply I1 times R2 is VR2. So I put that down next. So VR2 is equal to I1 R2. And that's equal to this, which is going to make this R2 over R1 times V in minus V out times the quantity R4 R3 over R3 plus R4. Do y'all agree with me there? That's the voltage on the R2 is shown, the polarity is shown, plus to minus. Do y'all agree with that, class? All right, now what's V out going to be then? I'll put it here. Somebody want to do this for me? What is V out going to be? Where do you always start? Ground, basically, because V out's taken from, I mean, you're right, you start from 0, but V out is plus to minus here. That's minus, and that's grounded, right? Start at ground, right? Well, if you start at ground, you got to go to this point next, because that's the only other ground there is, right? I come up here, the increase is just V plus, correct, class? It's just V plus. Are you with me? Right? V plus. What's the difference here? 0, right? V plus at that point, and it's going to be what? Right. Minus VR2. Now you put in the values for V plus and the values for VR2 right there in terms of the input and output voltage. So here, I'm going to get V out equal to V plus, which is V out times R3 over R3 plus R4. All right, that's V plus minus this, so it's minus R2 over R1 times the quantity V in minus V out R3 over R3 plus R4. Y'all agree with that? Yeah.
The VR2, I thought you were starting at the ground and working.
I did, but I'm looking, if I look at just VR2, it's just the voltage from here to here, right?
Yeah.
All right, I've got from here to here, it's just V plus. Then no voltage difference, right? And this would be minus that voltage, right? Because I started plus, minus
Okay, so you
VR2.
changed it to the other line.
Huh?
You changed it to the other line.
Well, yeah, because we want V out, right?
Yeah.
All right, well, I know this voltage, I don't know this voltage.
Gotcha, okay.
I have only one way to go. I've got to go over the known voltages to get to V out. All right, now, once we have this, did you guys do it down here? No? You did? All right, well, if you did it right here, he gives values for R3, R4, right? Does he or not? He does, right? Now, here's the deal. He just wants to find V out over V in. I can do it all by just moving things around. Look, I can take this to this side. I can take this times this to this side and get V out times something. Do you agree? And on this side, I would have just V in. Now the ratio of V out to V in, divide both sides by V in, and it would be that. Now numerically, if you can help me out here, we can do it easier. If you look this up, what is the ratio of R3 over R3 plus R4? Can you give me that? For the problem, what is R3?
That's 10.
And what is R4?
5.
So it's 5 over 15, is that right?
5K. Excuse me.
It doesn't matter, the K is going to cancel. So R3 is 5, R4 is 10, did you say? Or is
R3 is just 10, and then R4 is 5K.
That's extremely small. All right, so this is really, R3 is 10, right?
Yeah.
And this is over 5,010 ohms. So it's about 1 over 5,000, right? Agree? This is about 1 over 5,000 here, right? Correct? And what is R2 over R1?
5K over 100 ohms.
Let me write this down. R3, R4, R1, R2. Give me R1 first.
100 ohms.
100, R2,
5K.
R3,
10 ohms.
R4.
5K.
Okay. So R2 over R1, that's 50, right? That's going to be 5,000 divided by 100 is going to be 50. And then when I take R3 over R3 plus R4, here, I've got 10 over 5,010. And by gosh, that's really close. It's really 1 over 501 right there. So I can say, now I have V out equal to V out times 1 over 501 minus 50, right, times V in minus V out over 501. And now you can manipulate it as much as you want. And so if I take V in, it's one of those, I feel like fussing with, but I'm going to do it anyway. At this point, if we do this, I think I'll break this up a little more. I'll say that V out on this side equals V out here, 1 over 501 is the first term, and then I have minus 50 times that minus sign is plus 50 over 501 V out. And I have minus 50 V in. And now I can go ahead and I'll take minus 50 VI to this side, so I have 50 VI here equal to V out. And then it's going to be really 51 over 501 here, and it's going to be minus 1 is equal to V in, so really V out over V in, which is the forward gain, will be equal to 50 over quantity 51 over 501 minus 1. And somebody can tell me what that is if you don't mind. That would be the forward gain. They want the forward gain, don't they, class? For this one, in 928? Bryce, they want forward gain, don't they?
I think so. Are there any values of R that should be avoided?
Well, wait a second. Yeah, I can tell you one just looking at this. If you make all, see, this is our V out, right? I want to just show you how easy some of these questions are. These are like, there's what's the term? Low-hanging fruit. They're so easy. That's the thing. It's terribly easy to do this. R1 is 0 is a problem. Can everybody see anything over 0 is infinity? Y'all see that? That's a singularity. That's one problem. Now, if it's probably going to be a ratioing thing, but if you factor out the R3, R4, you're going to get 1 minus R2 over R1, and you're going to get the R3, R4 coming out. R3 plus, or R3 over R3 plus R4 coming out in front. So I'm going to say if R2 over R1 is R3 over R4, that's going to be a problem. Do they have that there? Because you're going to get a singularity. It's what values make these things go to infinity or 0 is what he's asking for. And I'm not going to ask that for you, but I'm just telling you that's what he's looking for. What can possibly go wrong is what he's saying. So if you look at this V out over V in, well, you can't have infinity and you can't have 0. So you look for values of R's, the ratios of R's that would cause that. Does that make sense to everybody? But the actual values that he gave, this should be the answer. Does he give you an answer for this one? Did you do this, Bruce? Did you work it?
The answer is negative 55.
What's that?
The answer is negative 55.
Did you do this? Is it minus 55?
Yeah, negative 55.7.
The answer is
Is that the answer in the solutions thing? It is? Okay. That's how you do it. Now, before I get on to what I want to cover today, does anybody have any other questions? These are good problems.
Like the capacitor problems.
Yes, we're going to do those. You have one in mind?
Just like any from the board.
Okay.
I don't mind buying it on these.
All right, anybody want to pick one, or you want me to?
There's a faster one. So that's 34.
Okay,
Yeah.
I'll pick. No, I mean, does anybody want to pick? No problem.
Just pick it.
I'm going to do problem, I'm going to do a couple of them here. I want to start with 539, and this has this configuration. I'm sorry, 939. My bad. Now let me say one other thing. I'm not going to ask you to. I'm probably going to give you problems that have a constant frequency. In other words, in the impedance domain or just resistors. I'm not going to ask you to solve differential equations. He has some waveform sketch there, and he wants the output based on the input waveform. Well, remember, if you have a differentiator or an integrator, it means you're going to do that operation on the input waveform. Follow me on that, class? I am not going to specifically ask you that. But I will ask you to analyze circuits that have capacitors at higher frequencies, at a constant frequency, and you're going to have to do them this way. So for this one, this is 939. He has Vn right here. It comes a resistor, which is R1. Comes into an operational amplifier. And this is grounded, which is nice. Then they put a capacitor here. And a resistor here. And they want V out with respect to ground. A classic problem. This is a circuit you're going to see, I see all the time, this kind of thing. So Vn, remember, it's always with respect to ground. That's plus or minus, and then V out. Now, the way you think about these problems, this is at a constant frequency. By the way, does he give the frequency in there for this problem? Does anybody got it in front of you?
20 microfarads.
That's the capacitance. 20 microfarads, okay? 20 microfarads is the capacitance. What is the frequency though?
It's not given.
They want it as a function of frequency, okay. All right, so now they want it as a function of frequency. I'm going to go ahead and say and make sure everybody understands this. Forget about the value of C for now. Just leave it C. Don't look there. All right, what I'm going to say is, what is the impedance of a capacitor? Does everybody realize the impedance of a capacitor is 1 over J omega C in the frequency omega? Everybody got that? Y'all with me, right? You have to know the impedance of an inductor and a capacitor. Now, if you have that, doesn't this look like just a block of impedance? We could say what this problem boils down to is that I have VI here, and I have some impedance Z1 here, regardless of what it is. Then it goes to the negative portion of the input. Then there's a positive terminal that goes to ground, and here there's some net Z2 that comes to the output. When I look for V output from plus to minus to ground, what I can say is this, and this goes back to the most basic type of circuit. If this is plus to minus ground here, I can say the current flowing here, now just look, that's 0 volts, right? That's 0 volts. Current here is just VI over Z1. Agreed? It's very straightforward. There's nothing tricky about this. Correct, class? If I have that current, I know none of that current flows into the negative terminal, correct? All of the current must go this way. Agreed? Everybody? If all the current goes this way, this voltage, V2, is simply going to be that current, and I'll level it, that's I, times Z2. And that means V2 is VI times Z2 over Z1, whatever that is. We'll get what the value is in a second. Do you all agree with that? Now, if you look, what is V out going to be? Well, I start at ground, that's 0, right? Here to here, that's 0, right? It's minus V2, which is minus Vn times Z2 over Z1, agreed? And that means V out over Vn, which is the forward gain. That's the forward voltage gain. I'll just put AV here. That's going to be equal to simply minus Z2 over Z1. I put up a template because I want you to see for any impedance. Doesn't matter what the impedance is. Yeah.
Why isn't I1 equal to VI over Z1
It
or
is.
Z2?
Not Z1, Z2. VI1 is this current, right? That current is this voltage minus 0 over Z1, right? It's a current. I is a current, right? You all with me on this, class? All right, keep working with me now. It's not hard. Just follow the general trends. Now, look at this. The Z1 in my equation right there, what is it for our problem? Come on. Where's Z1 from?
R1.
It's just R1, right? Now, what's Z2? Well, that's right. And so what I always say is if you have a capacitor impedance in parallel with the resistor, and they have the most basic form is where you have a 1 over J makes it, just take 1 over the first impedance, which is going to be just 1 over R2 plus just J omega C. Follow me? I took 1 over each of those elements. Correct, class? Now, if you want to, you can multiply top and bottom by R2, and then you get R2 here, and it's going to be 1 plus J omega R2 C2. All right? Or C1, pardon. There's only one C, so it doesn't matter. Now, that's Z2. So now it can say my voltage gain here, AV, will be equal to minus Z2, which is that R2, over 1 plus J omega C times R2, over R1. Or you can just say minus R2 over R1 times the quantity 1 over 1 plus J omega C times R2. Now let me tell you, when you plot this, I'll tell you what you're going to find if you do a magnitude plot. I'll try to sketch it here. If this is versus omega, and say it's really the log of omega here, so the paper would take the log, it would be something like this. This could be 1, 10, 100, 1,000, 10 to the 4th, and so forth. So the paper takes the log here, and on this axis, if you plotted 20 times the log of the magnitude of the voltage gain, what you get is this. First you start, put omega equal to 0. At 0, what do you have? Omega 0 is DC, right? Well, this term is just 0. I have 1 over 1. R2 over R1 is the ratio. If I take the magnitude of that, it's just, get rid of the minus sign. This would be 20 times the log of this. So this starts in at 20 times the log of just R2 over R1. I'm doing this for a reason. MEs and aerospace for sure, they're going to see operational amplifier characteristics in the frequency domain. Almost always, this is the log of F or the log of omega. And the vertical axis is going to be 20, usually it's 20 times the log of the voltage gain, all right? It's almost always dB scales. And you're probably, engineers are used to dB scales because you've got to do that because you get orders and orders of magnitude of difference in values and things. So taking the log of it brings it down to something where the numbers are only maybe a factor of 10 at most different. When I take a look at this, it's gonna stay at that value, this is just the magnitude of AV, until I hit this point. When omega times C times R2 equals 1, then I have 1 over 1 plus J. Well, 1 plus J has this odd property. Its magnitude is 1 over the square root of 2. That's called a 3 dB frequency. How many have heard of 3 dB frequencies in here? And mechanical engineers use this. It may have is it called a cut frequency, or what's the term in mechanical engineering?
Cutoff frequency.
Cutoff frequency. This is the first break frequency or cutoff frequency where the amplification starts going down. So when it hits this, wherever it is, it's going to stay there. Then it's going to hit a frequency, and that frequency is going to be when omega R times C, it's R2 times C, equals 1, which would mean omega is 1 over R2C, or F is 1 over 2 pi R2C. That's the curve. Then this thing will start coming down at a rate of minus 20 dB per decade. This is beyond the scope of this class for some of you, but it's important for MEs and aerospace engineers. You're going to see plots of operational amplifier characteristics where they're going to hit a frequency, break frequency, cutoff frequency, and it'll start coming down as 20 dB per decade. How many have seen this when you've done op-amp designs? Which laboratory is it?
It's, well, you use it all the time in systems, dynamics, and
Oh yeah, systems, sure, you're going to do this. Do you use op-amps in there or not?
we just started getting into that.
All right, you got,
Low pass filters.
yeah, you can use operational amplifiers for active low-pass filters, but it's done a lot. But I'm going to tell you, you're going to see this a lot. And I'm trying to explain it to you in the most basic terms. Ideal op-amp, the way that a lot of times that they'll show you the characteristics for the circuit. I mean, this is the characteristics for a circuit. They'll have an operational amplifier, and then what they'll have is a plot like this to show gain. Now, one last thing that's a little bonus there, it's called gain bandwidth product. You're going to hear that. That's a figure of merit for an operational amplifier. They take the actual gain of an operational amplifier when it's used in a circuit like this, and they multiply it by the actual break frequency. It's called the gain bandwidth product, and the larger that is, the better it is. It means the further out this break frequency is. All right, that's bonus, and it's actually just for the operational amplifier without the external stuff, but I can't get into that now, and it's my habit to get into things I shouldn't sometimes, but I'm going to try not to. All right, that's one. The next one, we can actually look at 9.43, but I'm going to leave this part up here. And if you have a specific question, ask it.
For Z2, if R2 or 1 plus J omega C2, then we put the R2 at the bottom.
Well, what I had, because I had 1 over R2, right? I multiplied top and bottom by R2, so I get R2 on top, and then I have just 1, because 1 over R2 times R2 is 1, plus J omega C R2.
Okay, so the equation is called J omega C and the resistance on the bottom.
Mm-hmm.
Okay, because just initially you didn't have the R2 multiplied by the C2, so.
I think I put it in there in the second part, though.
Yeah, okay, I was just making sure.
All right. Now, this next problem is one that I'm going to do is, if there's something else you want to see, let me know, because I'm doing these as I see. I guess it's in your best interest. I'm not trying to go way out and get real complex problems for you. So this is going to be 943. Let's say plot the magnitude of the closed loop gain. That's just, it's really the gain versus frequency. But I won't ask for plots. I want to do the analysis of this one. This is Vn here. Then they have R1, and they have a capacitor here. Then they have this grounded. It's a pretty good problem, actually. So they want to know, I want to know, V out over V in. I want to figure that out. Take a good look at that just for a second. Stare at it. I want everybody to ask himself just one thing. Does that look like it fits the model right here? Y'all see it does, class? It sure does. There's a single impedance between V input and the negative input terminal, right, for between V, and there's only one connecting path between the negative terminal and the output terminal, right? Y'all see that? So what would Z1 be, people? Just look at it.
R1 plus 1 over J omega C.
That's right, R1 plus 1 over J omega C1, right? That's it? What is what is Z2? Well, take a look at it. Now, you'll notice it has the same form as the one before, right? And this has an impedance of 1 over J omega, well, J, in this case, C2 omega, right? Or omega C2. Agreed? Now, when you got two things in parallel, two impedances in parallel, you can either multiply them and divide by the sum, or you can take 1 over the first impedance for 1 over the second impedance. It's easier to do that 1 over the first over 1 over the second in this case. So it's 1 over R2 plus J omega C2. Follow me? Somebody asked about this. I'm going to go through it slow. Now, I don't like the 1 over R2 for a lot of reasons. So now I multiply the top or the numerator and the denominator, numerator and denominator by R2. And now I get R2 over 1 plus J omega C2 R2. Got me on that one? I'm just doing it to make it easier to see the property of it. Now when I take a look at that, I'm going to erase this now. I can say this is minus Z2 over Z1, or it's minus Z2 would be equal to R2 over 1 plus J omega R2 C2 divided by Z1. That's Z1, so now I take 1 over R1 plus 1 over J omega C1. And I can divide top and bottom by R1 in this one. You're not going to like this, but if I divide top and bottom by R1, then I get R2 over R1, and here I get a 1, and then I get an R1 here, and I also get a minus J. 1 over that. This is not, I've done these kind of things over and over again. That's the reason I know what to do here. But what I'm trying to get is a 1 by its lonesome here, next to this number. Because I know the break frequency will be when that is equal to 1. All right? When 1 plus J1 occurs, that's a break frequency. Here I know the break frequency will be when this goes to 1 as well. The thing about this has a negative J sense to it. All right. Now we can multiply these out if we want, but this will be the actual, this is the voltage gain ratio. And you can see when omega, this one you might need to multiply out to actually see everything. But let me just mention, there's a couple things about this that are unusual. When omega is 0, what's the voltage gain? Just take a look at that. What's the problem? As omega is going to 0, what do you see happening here? That's going towards infinity, right? And the voltage gain here looks like, as omega goes to 0, it's going to infinity. In fact, it does. The reason is, if you think about this in a limit, if you're at DC, or at the DC, right? The capacitive impedance is overwhelming, it's so large. Well, that means this basically looks like a single capacitor. this looks like a single resistor. So at omega, as omega goes to 0, the circuit reduces to this. That's because the impedance here is an infinite, right? And this resistance, that value is much, much less than the impedance of the capacitor. Now for this one, it's minus Z2 minus R2 over that, or it's really V out here over Vn is approximately equal to just, it would be J omega, or minus J omega R2 times C. And you can see as omega goes to 0, that's going to infinity. You all see that, class? So at 0, you got a problem, and also as omega goes to 0, sorry, the voltage gain goes to 0 as omega goes to 0, my bad. And also, as omega gets very large, the voltage gain goes to 0 as well. This is a little more advanced, but I could ask you for a single value there. Right, I mean, for a given frequency, what it is. All right. You want your quiz Friday, or do you want it Monday? Doesn't matter to me, but I know it's a Georgia game.
Monday.
How many want it Friday? Hold on. How many want it Friday? One hand. How many want it Monday? One hand. The Mondays have it. It will be on Monday. I'm asking just for a vote. I do this because I know we got a lot of people. Hey.